Okay, hey everyone, Coding Heaven here. I'm back to talk about Factorial again. Second video about Factorial. Today we're gonna do recursive Factorial. Recursive Factorial is so much more interesting than iterative Factorial. I guarantee that. So, what are we gonna do? You remember last time I defined recursive Factorial as like a function that is defined in terms of itself, or like in terms of a function that is similar to it. Now that is recursive factorial. So like that's what we're gonna do today. I gave you a theoretical definition, but today I'm gonna show it in practice. I'm gonna show you what it is when it comes to factorial, and it's very interesting. So listen closely. So let's like, oh my god, I moved it again. Keep on moving it. So annoying. Okay, recursive factorial. Oh my god, that's a horrible line. It's even worse one. Okay, recursive factorial. I was like thinking about making this joke so that I shouldn't put exclamation interrogation point. I should put like exclamation point because like that's the factorial symbol. But I decided not to make it because it's a bad joke. Okay, so I defined last time that factorial is equal to this. So times. So it's basically the product of all the this positive integers less than or equal to the input n. So I gave you guys an example. It was 5 factorial, 5 times 3, oh my god, 4 times 3 times 2 times 1, which is 120. We verified this last video, so thank god I got that right. It would have been embarrassing. So keep in mind that we stop at 1. Stop at 1. Stop at 1. This does not exist with the way we're defining it here. It may exist with another function called the gamma function, which of course I won't be explaining today. It's very deep in math, but this is not defined in the way we are defining it today. Even recursion doesn't work with it, nor does iterative way of calculating it. So let's think. So what is recursion again? I explained it to you guys, but how does it apply to this case? It's kind of hard to figure it out, so I'll just show you something. What is n minus 1 factorial? What is that? If we follow the definition, it's gonna be the input times the input minus 1 times the input minus 2, all until 1. So here the input is n minus 1. So it's gonna be n minus 1 times the input minus 1. N minus 1 minus 1 is minus 2. Then n minus 3, and then dot times 1. By the way, these are 1s. These look like, a lot of people tell me they look like 7s. It's so mean. Anyways, these are 1s. You stop at 1. So, like, where have you seen this before? This is really suspicious. It's really familiar. It's right there. It's right here. This right here is exactly this. What? So this is the essence. This is like the beauty of factorial right here. So you can define n factorial as n times n minus 1 factorial. This is a recursive definition of factorial. So let's brainstorm this. The reason I was able to put this is because if this right here, all of this all the way down to 1 is equal to all of this down to 1, because it's the same thing, n is here. And if this right here that I'm like highlighting around is equal to this, therefore I can substitute this for this. So I can just plug this in here instead of all of these. So it's going to be n times this equals n factorial. As easy as that. This is awesome. And like, it's also so intuitive. It's like so intuitive. Like, if we think about it, 5 factorial, 5 times 4 times 3 times 2 times 1. What is this? What is that? So basically 5 factorial also equals 5 times 4 factorial. Sorry, 4 factorial. So, but what is 5 factorial equal to also? What is this? 3 times 2 times 1. So 5 factorial also equals 5 times 4 times 3 factorial. What is it also equal to? 5 times 4 times 3 times 2 factorial. And continue like that. So this is the power of recursive algorithm. The definition is using the function itself to define the like the way of calculating it. So that's fun. That's incredible. It's very powerful. So let's think about coding it now. How are we going to code this? Let's put the math aside. How did we code this? This one we coded it with a for loop. We coded it with a for loop. How are we going to code this? Let's think about recursion. Recursion, because this is a recursive algorithm, so it's recursion. Recursion needs 2 elements, of course. Use function in the definition. The definition, which what we use the function itself in its definition. There's one last thing. I told you guys it stops at 1. If we give this exact formula to a computer, it's never going to stop at 1. An integer can go down to the negatives. So it's going to go n minus 1. Is going to at some point it's going to go down to 0 times negative 1 times negative 2 times negative 3 all the way to times negative infinity. At some point we have to stop it ourselves, because the computer doesn't know when to stop it. The computer doesn't know he has to stop it. So how are we going to stop it? What we're going to do is we're going to define an initial value, and that initial value is 1. Factorial equals 1. This is the initial value right here. And of course this is intuitive, so when this gets to 1, it's just going to return 1. It's not going to return this whole thing. It's just going to return 1. Now let's test that. Let's test that right away. I'm excited. This is so cool. Let's test that. Let's jump right into Eclipse. Let's open up Eclipse. Let me close this. So now let's jump. We did iterative factorial last time. So let's do recursive factorial. Public, no, not void. Static long recursive factorial. Of course, we're going to take the same input as iterative factorial. And how do we do recursive factorial? So how do you do that? So let's think about it. I told you guys we can do it with one line. I won't be doing it with one line in this video. I could do it with one line. Actually, you know, I'm gonna show you guys with one line, but I won't show it to you now. I'm going to explain it first before I put it one line. So remember I told you the initial value. So n equals 1. We need to, if n equals 1, we just return 1. And else, if n doesn't equal 1, what do we return? Remember, we return this function right here. This function right here. So we return this exactly. So we're going to return n times recursive factorial of n minus 1. This is magic. Not even kidding. This is magic. So we're done. That's it. That's recursive factorial for you. We're done. Let's test it now. Wait, we can't test it right away. We need to put here. We need to put recursive factorial dot recursive factorial n. I'm excited. Okay, let's do this. Let's run it. See if we did it properly. We did it properly. There you go. And recursive factorial, I think it's quicker. I don't know if it's quicker. 'Cause I'm not even studying computer science yet. I'm still in. Technically, according to the American system in high school, I'm in Canada. I'm in Quebec, so like it's a different system. So 10, 15, so it works. Perfect. Okay, this is perfect. This is fantastic. Now we're done. The factorial calculator. If you guys want, I can do this. Static string big factorial. Now this, you guys are gonna have to request it in the comments because it's a complicated process. It's very complicated. It's very complicated, and it basically uses strings because strings can hold a much bigger number, but in text than an int or a long. So we're gonna use strings to be able to calculate factorial of big numbers, like huge numbers. And we'll be using string manipulation to do that. So that's really exciting. Tell me if you want me to do that video. Next mathematical algorithm we're probably gonna be doing is Fibonacci, yes, Fibonacci. Fibonacci is awesome. So thank you everyone for watching. This was very cool. Thank you for watching. This was very nice to do. Thank you everyone for watching. Like and subscribe if you like these mathematical algorithms, and have to the next time.